Okay, so good afternoon or good morning to our guests from international guests. I'm happy to host today here Professor Diego Ghezzi for the BIU Vision Seminar. So Professor Diego Ghezzi holds a Medtronic chair in neuroengineering at the EPFL in Lausanne. He received his master's in biomedical engineering and a PhD in bioengineering from the Politecnico di Milano. From 2008 to 2013, he completed his postdoctoral training at the Institute de Italian Technology in Genova, at the Department of Neuroscience and Brain Technologies, and he was promoted then to a researcher. Then since 2015, he was appointed in a tenure-track assistant professor of bioengineering at the EPFL in the Center for Neuroprosthetics and Institute for Bioengineering. His field of interest are diverse and they are multidisciplinary, highly multidisciplinary, focus on optoelectronic interfaces, neuroprosthetics, mainly visual prosthetics, optical stimulation, microfabrication, and some other project aimed at vision restoration or neural restoration of tissue. And so without any further ado, let's all thanks Professor Ghezzi, and we can start. And if you have any questions, if it's a burning one, then we can stop. You can send an email, a chat. If you want to hold it until the end, we will have a lot of time to discuss. So please, Diego.
Thanks a lot, Yossi, for the very kind invitation, and thanks to everyone which joined this virtual talk. So as Yossi introduced, I will present our research activity of my lab, mainly focusing on our activity on developing a retinal prosthesis for artificial vision. But then what really I would like to do is to show the motivation that moved us into this activity and the idea that we generate, and see how those ideas can be translated into a new project that we recently started, which is more focusing on cortical stimulation or cortical visual prosthesis. So as you can already understand, I'm going to speak about the electrical stimulation of the retina. And as you know, this is a very old story. It started many years ago, actually, at the time of Benjamin Franklin, where immediately after a physician in France, in Montpellier, tried to electrically stimulate the occipital pole of a blind volunteer with the idea to restore vision. And from there, which was like in the 1755, there have been many experiments. And I think really the one important milestone in the field was reached in the 68 by Brindley and Lewin. Basically, they implanted two volunteers. You see on the top here, the first volunteer with a bilateral cortical visual prosthesis. I believe, I might be wrong, but I believe this is the first example of a permanently implanted cortical prosthesis. And then the second patient, a few years later, received a bilateral implant. And you can immediately recognize here the subject, which is pointing to the end, because it's describing the percept that she's having upon electrical stimulation. Now, in our field, we know very well, we call this phosphine. And that's, for me, it's an important step, because since then, many activities started. And as you know, probably, most of them were recently focused on developing retinal implants, so not cortical, even though there's been now a new push on cortical implants. But what is more important to highlight is that probably at this point, we have realized that the goal of restoring vision is still very far. It's extremely far. And therefore, in this talk or in general, I prefer to talk about artificial vision, which is this sort of different form of vision that is generated when we applied an sort of unnatural stimulation to the visual system. Could be electrical stimulation, could be mechanical stimulation, optogenetics, or whatever. And here is represented for a retinal implant, just because it's very easy. But the main concept that everyone agrees on the definition is that when one point of the visual system, let's say a subset of neurons, like in the retina, are activated, for example, electrically, the people or the blind volunteer perceive this sort of dot of light, no, that we call exactly phosphine, which are known since hundreds of years. And the goal is that to use this dot of light to sort of create perception of shape, objects, contours, letters, and so forth. So that's what we call artificial vision. Now, of course, that is a very ideal representation where electrodes are activated in the form of the letter E and phosphine appear as the electrode position. In reality, we know that this is far from the reality. Depending on where these electrodes are located, in which portion of the visual field, in the retina, in the cortex, in the optic nerve, even in the retina, depending on the location, phosphine might be different in size, shape, colors, and so forth. So probably people have perception which is a little bit distorted, more similar to what's represented here. And somehow we hypothesize that with time and learning, or what we in other fields we call neurorehabilitation, people can learn how to interpret this new acquired form of vision, which is artificial vision. So say that artificial vision can be useful for helping people that are blind. Now, here it's the second important aspect that motivates, or somehow it's very important to me when I started into this field, is that when you look worldwide, you know, this is now data from 2020. There are 43 million people blind worldwide. But of course, being worldwide, roughly half, these left parts, are blind people because of preventive disease that could be either prevented or treated. You see cataract, uncorrected refractive error, trachoma, and so forth. Now, the remaining half, they have blind because of a variety of diseases. Actually, it's a very complex medical condition. Of course, the leading one is glaucoma, that there is age-related macular degeneration, and then many others. So this diversity is it's very interesting for people in the field of artificial vision, or more broadly vision restoration, because it means that it's so diverse that actually there will never be a single approach that will help blind people. You always speak about a variety of approach, or several types of approach. And even in the prosthetic field, that is very interesting, because some of these diseases, like age-related macular degeneration, or for example, inherited retinal dystrophy, they affect the early retina, so the photoreceptor. So that's became interesting, for example, for retinal prosthesis, but there is a huge cohort of people that are blind because of many other cases. Number one in the list, glaucoma, but could be diabetic retinopathy, optic nerve disease, trauma, and so forth. And of course, this needs to be addressed with other technique, not certainly with retinal implants. And of course, the other aspect to keep in consideration is that it's a type of condition that affects at every age, and somehow the prevalence of those diseases, it's age dependent. For example, ERD affect most of the blind people are in working age, AMD in older adults, and so forth. So that is a very complex scenario, which require not necessarily complex solution, but at least a variety of solution. In the prosthetic field, we typically classified visual prostheses in 3 to 4 categories, depending on the position in the visual pathway. We have retinal implants that I will talk mostly today. There is the possibility to implant the optic nerve. There are cortical implants, and the fourth one, which is still a possibility, although it's never been explored in humans, is targeting the thalamus, the LGN. So, but let's start with a retinal implant. That is the main part of my talk. So I will present this work related to the development of the polyretinal device. So first of all, what was the motivation? Well, the motivation, obviously, if you want, the application is for a retinal prosthesis, is for condition which affect photoreceptor. In particular, our motivation was for those conditions which induce peripheral vision loss and ultimately total blindness. So our device is currently thought for people which are totally blind, so no remain functional vision, and eventually in future for people which have peripheral vision loss, or so-called tunnel vision. The reason I mentioned these categories is because what we really pushed over the past 8 years was to develop a device which was large enough to cover a very wide surface of the retina. I will explain a little bit later why this concept is important. But what you can see here, it's again, probably you know, is the Argus 2. And it's a very beautiful picture. That's why I use it often in my slide. And you see what to me are the three most important design parameters in a retinal implant. So those are the engineering parameters. No, you can play with the number of electrodes. The Argus 2 had 60. You can play with the distance, the dimension, and therefore the distance of the electrode. In the Argus 2 was roughly 575 micrometer. And then by combining the number and the distance, you get to the covered area, no? Which turns out to be the visual angle of artificial vision, which for me, it's really the most important factor. I came to believe years ago that in order to improve the quality of life of patients implanted with those devices, yes, resolution is important, but what was really important was really to try to build a device which had a larger coverage of the retina, so increasing the visual angle. So that was my main motivation. And in fact, the motivation of my work was not necessarily to build a device, which we did, but in the end, my long-term goal is to really prove that the visual angle matters for this patient with implanted device. And of course, we didn't want to do that by spacing more the electrodes, because of course you can increase the size by spacing more the 60 electrode, for example, but this will reduce the resolution if you wish, but was doing it not at the expense of the electrode resolution. Why it's important? Part of our not being able yet to implant our device in patient, some years ago we started trying, and that's also, I think it's interesting from this perspective of validating device before reaching a clinical trial. We started work with augmented reality and virtual reality, which is now they are accessible to basically everyone. We see here a typical experiment where we monitor several parameters in biophysical markers, and then we try to simulate the perception of people with implanted device. No, we do that using models which have been generated by others group. In particular, what you will see in the next video is the simulation we doing a normal task, which is going outside of this door, which is my office. According to the model of the Argus 2, which was developed by Michael Baylor in the States, is the pulse to percept model, if some of you knows. So now you see the appearance during this task in artificial vision or with phosphene. You see it in this part of the screen. Now, of course, the subject here can perform the task very easily because knows very well the space, but frankly speaking, what is clear is that it's impossible to recognize anything. Now, this is a simulation. Of course, there are a few things to be said. The first thing is that patients have much worse vision in the sense that here phosphene are very geometrically aligned, all the same size. They're all appearing, all the 60, but typically in patient is not the same, it's more complex. And on the other hand, the factor that I would try to convince you that really matters in order to try to perform a task is the area of artificial vision, so the so-called visual field. The problem in this task is that what the person is trying to do is try to walk, to ambulate, avoid obstacle at a normal speed. Now, even with this 60 electrode, if you will take, I don't know, several minutes to perform the task, ultimately you might do it, no, very slowly by scanning the environment. Ultimately, you can recognize where you are, but this takes too long. And that's why, in my opinion, it's really the times that matters. Now, we want to enable people to perform tasks at a reasonable speed. And that's where the visual angle became very important. So this is why we generate this device, polyretin. Now, I will go very briefly on the technology, but you are free to ask questions. So it's a 2 centimeter wide device. It's hemispherical to fit the curvature of the eye. It's about 14 millimeter in diameter, the active area, which is this area with the electrodes, the pixels. So it's cover, roughly speaking, 43 degrees of visual angle. That is calculated numerically. It's not being validated experimentally. Pixel or electrodes are 100 micron in diameter, and the distance between electrodes are 120 micron, the so-called pitch. And there are 10,500 pixels in the device. Each pixel is a photovoltaic cell, so it's composed by 2 electrodes, the anode on the bottom and the cathode on the top. And in between, there is a semiconductor which absorbs light and generates charges. So it's a photovoltaic device, if you wish. So the charges are generated in the semiconductor, then they split because it's a mix of 2 materials. At the interface between the 2 materials, charges split. positive charges or holes are attracted to the anode, and negative charges or electrons are attracted to the cathode. And the pixel is immersed in the saline solution, so the field is closed in the saline solution, as any other anode-cathode based electrical stimulation. And there are 10,000 of those. So the idea is to have a photovoltaic device. Today, retinal prosthesis photovoltaic devices are very common, including the works done by Yossi many years before me. So it's the framework is that you need to have a camera which take images, a processing unit, and the microprojector that project the light back into the eye at the right color, frequency, and pulse duration, so that each time one pixel absorbs light generates charges and stimulate the retina. So practically speaking, there are no wires to implantable stimulators, but it's all driven by light. It's a passive device. There is no powering. Each pixel became active capacitively when it's illuminated. So the device can be manufactured with standard clean room fabrication. It's a fabrication done on, this particular type is done on PDMS. So we make a PDMS membrane, so it's very stretchable, it's very thin and elastic, and we make pixel on top of it. Here you see the pixel on top of the PDMS membrane. The PDMS membrane is it's 100 micron thick, so it's extremely elastic. It can deform. You see it here when you stretch it linearly. So basically, you pull it apart. Now you see that the pixel row are teared apart according to the direction of the force until a certain point the PDMS breaks. So once you reach 100% of strain, the PDMS break. But it's very interesting that PDMS breaks. Pixels are very well protected and remain intact even upon breakthrough. It's very important that it's elastic because to make an hemispheric device, what we do is that we take this photovoltaic interface and we stretch it and bond it already onto a preformed hemispheric lens. And by doing that, we stretch a little bit by 3% the device. So we are very well within the stretching capacity. And then after bonding, we basically get our device. So over the years, we characterize the device mostly in vitro, ex vivo. We use blind retinas. We take retinas from this animal model mouse, the RD10 mouse model, which is a model of retinitis pigmentosa. They lose retinal photoreceptor. Here you see on a microelectrode array, the responsivity of neurons upon light stimulation. You see at day 16, the animal is still very well sighted. So the degeneration, it doesn't take place yet. At P43, so 1 month after birth, you start to see that there is less response. And then after P60, so 2 months, you see that there is no more response. And this sort of rhythmic activity start to appear. This is very common in this animal model, this sort of spontaneous rhythmic activity. So we want to work in a condition that the animal is considered to be blind, but without this strong rhythmic activity, because it might mask effect of electrical stimulation. So we focus our experiment between 96 and 130 days of age. So 3 to 4 months animal. And there is no response even for very strong light irradiance, as you can see from this graph. So we took the explanted retinas, we put it on top of the device. We use microelectrode to record from retinal ganglion cell on top of the illuminated pixel. So we have a pattern stimulator to illuminate only 1 pixel of the device. And we record retinal response. You see here, this is what is so-called network-mediated response. Now, it's very delayed from the onset of the pulse. The light is a green pulse of 10 milliseconds. Here you see clearly the stimulation artifact. And then you see this huge response that comes from the activation of the network, which is composed by bipolar cell, clearly, providing the excitatory contribution. But don't forget that very close to retinal ganglion cell in the epiretinal side, there are also amacrine cell, which provide lateral inhibition. So this huge gap between light and activities, we believe, is mostly mediated by amacrine cell activity. So when we measure indirect, so this network-mediated activity versus the direct stimulation of retinal ganglion cell, is very easy to separate because network-mediated comes several milliseconds after the light pulse, while direct stimulation of retinal ganglion cell occurs 1 or 2 milliseconds after the pulse. So you can separate temporally those. You see that our device is very efficient, according to the irradiance, to activate the network-mediated mechanism, but not so much the direct activation of retinal ganglion cell. And that came down to an easy explanation. There are two sort of a combined explanation for it. One is represented here from an experiment made by the group of Daniel Palanker in Stanford, where he demonstrated that epiretinally, once the duration of the stimulus exceeds a certain threshold in time, so in milliseconds, which the threshold being 8 milliseconds, hour is 10 milliseconds, the light pulse, the network-mediated stimulation is favored compared to the direct stimulation. So it's easier to generate spike by the network rather than by the direct stimulation, the retinal ganglion cell. That is the first observation, which was done for rectangular electric pulses. The second observation was done by the group of Jean Whelan, working with Argus 2 patient. Here is a figure where they show that the same patient with the same electrode, when they use the classical Argus 2 stimulus, so 450 microseconds, so very short pulse with rectangular waveform, the patient perceives very arcuate phosphine. This distortion is due to the activation of fibers in the retinal ganglion cell fiber. But when in the very same patient and very same electrode, they moved into a longer stimulus, so plus minus 50 milliseconds, and due to the duration of the stimulus, they changed the waveform. This is a limitation of the stimulation to this sinusoidal waveform. The phosphine suddenly became round, which implies that there was less fiber activated. And it's very interesting, this part is not the duration. I mean, increasing the duration already, Daniel Palanker showed that favors network-mediated stimulation, but also this shape, this non-rectangular waveform became very interesting because in our experiment, and then in this paper, you can see more details about it, but here I just summarize. We compare the activation of retinal ganglion cell with a rectangular waveform. This is a voltage pulse. We drive electrodes in voltage, in this case. This is a voltage capacitive pulse, no? Which gives rise to these very sharp capacitive current peaks. And we compare it with respect to the photovoltage generated by our polyretina pixel with the same 10 millisecond green light. No, the photovoltage has a more capacitive profile, especially in the discharging. You see that it doesn't discharge sharply, discharge slowly. We call this sort of capacitive-like stimulation. But when you compare for the same amplitude, the exact same retinal ganglion cell, you see that the rectangular is much less efficient than the capacitive one to activate the network-mediated activity, in line with the previous results. So I think it's a combination of duration of the pulse and waveform of the pulse that lead us to have this strong epiretinal network-mediated stimulation. So with that in mind, we made to the second experiment. Since it's a network-mediated stimulation, it's reasonable to consider that more than one pixel will stimulate the same retinal ganglion cell, because in fact, what we show here is the electric receptive field of a given retinal ganglion cell. So we record from a retinal ganglion cell, but if the receptive field, so the number of bipolar cell and the macrine cell, this retinal ganglion cell receive input, and we know in mice receptive fields are typically large, it might be possible that more than one electrode activate the same retinal ganglion cell, which is represented here, no? This electrode max, it's the strongest in terms of activation response of the retinal ganglion cell, but also neighboring pixel activate response in the same retinal ganglion cell. Like will be obvious in a subretinal stimulation, or if you have one electrode here and another electrode here, those bipolar cells might converge to the same retinal ganglion cell. So it's sketched here now. One pixel activates a pool of bipolar cell, another pixel activates, this is a sketch, obviously. Another pool of the same bipolar cell, but these two pools might come to the same retinal ganglion cell. This is a little bit the paradigm that we have. And because of that, we thought that then the retinal ganglion cell should be able to distinguish between the two different subunits. And this is the experiment that we run here, no? Because if network-mediated stimulation, we should consider that adaptation of the Troxler effect will take place here, the famous desensitization. So when you repeat stimulation with the same electrode in the same retinal ganglion cell, this is an average of many retinal ganglion cells, you see at the first stimulus, the response is strong, and then with the repetition of the pulse, the response almost fade out to baseline activity. These are 10 pulses at 5 Hz repetition rate. Higher is the repetition rate, faster is the fading. That is, it's known due to the bipolar cell desensitization. And now, which is an obvious experiment, which we can call it two-point discrimination, when you switch to another pixel, so you do the first set of 5 pulses with the orange pixel, let's say, you see the desensitization, but when you switch to another pixel, which still activate the receptive field of the very same retinal ganglion cell, you see that the response is recovered because you stimulate a different pool or a partially different pool of bipolar cell, not yet desensitized. And then the response goes back again, and this can be repeated over and over. So this is a two-point discrimination test, which in the end tells you that the spatial resolution of the device is equivalent to the pixel pitch. And in fact, the more obvious test to do this now, now that we know, will be the pattern reversal. You can repeat exactly the same thing. Green bars are light, black bars are not light. You know, the paradigm, you reverse the pattern, and then you reverse the pattern. The retinal ganglion cell fade out during the stimulation with the same pattern. Then as soon as you reverse the pattern, there is recovery response, and so forth at the third reverse. That's with bars with dimension equivalent to the pixel pitch, 120 micron, and you can repeat the experiment by modulating the dimension of the bar, like you will do in a normal visual acuity test. And you see that here, the particular look at this plot that is the most interesting. There is the grating resolution of individual cells measured, and you see that most of them peak around 100 and 120 micron resolution, which is the obvious one because it's the one related to the pitch of the electrode. Few of them integrate finer bars, and few of other they respond to larger bars. This is a classical distribution of those cells. But obviously the spatial resolution peak, it's equivalent to the pixel pitch. So with that results, we moved in vivo. Now, one of the tricky components of the device is that it's big, and being big is good because larger surface area, but the question is how you're going to put it in the eye. That was the main problem, no? And that's why at the beginning of this experiment 8 years ago, I started this project with a surgeon. We worked together, we had the idea together. I will mention him at the end. But the important thing is that this device is fully elastic, not only the membrane, but it's like an intraocular lens. You can roll it. In fact, we were inspired by intraocular lenses. You can roll it, you can release it and recover its shape. That is not just a lens because there are elements on it, there are pixels, but what you can see here in those set of slides is that no matter what you do, on the top you see that you can fold the device 4 times, but the pixels don't crack. Here you can pinch it with a forceps, but still before and after pinching, you see the device are perfectly intact. So the device is extremely robust despite manipulation. So therefore with this we thought, okay, then you can insert it, roll it. At the beginning, we started by taking with forceps. No, you can see here, those are plastic human eyes that we use at the beginning to check the damage on the device. You can insert it in an aperture which is 6.5 millimeter, like in the Argus 2, if you wish. And then we went into design several type of injectors. This is the last one that we manufacture that was tested in the in vivo experiment. So you see, you can roll it with a forceps. Anyway, it doesn't damage. Then you insert it into these specially designed injectors, which is lubricant-free, so that there is no need of lubricant. There are those 2 wings that keep the device rolled, and then you can eject it. And the device, in particular the pixel, they are not damaged. You see it here before is this one, and after injection this, and you see it's the very same spot. You see here this part is really the very same spot that we take before and after injection. There is no damage. So with that concept, we went in vivo. Obviously, having a large device means that for us, all testing in small animals were somehow restricted, which would have been very nice to test first in rats or those kind of animals. But being a large device, we went to go into large animals. Here we choose the mini pig in particular. So here you see some snapshot of the surgery just to give you a glimpse of the surgical practice. We do standard lensectomy and vitrectomy. Then we make an incision exactly here. So it's a corneal incision in the end. It's 6.5 millimeter. Then we insert the injector here, you see, and we inject the device, which then is fixed in place with retinal tacks. Now, for this set of studies, we use retinal tacks, 2 for the device. We couldn't use standard one. We had to make our own, which are highlighted here. That is one of the, somehow I anticipated, it's one of the weakness of our approach so far. Retinal tacks, we know they are not good for this type of devices. even though we can fix the device in place, no, we know from the experience with the Argus 2 that over time, retinal tacks became loose. So that is a point where we need to work on and try to figure out something better for the attachment. But so far, that's what we have. So here you see an echographic image on the eye. You can see that there is no more the lens. We have to remove the lens for the lensectomy, and we didn't replace it. But what you can, that's why OCT was not performed. But you can see with the echography the retinal implant here, which is very well attached to the retina. So then we tested our device. I forgot to mention that the mini pig was made blind. We had the procedure to make blind the mini pig. I don't have slides, but details are clearly in the paper. So if you're interested on that, there are all the details in the paper. So mini pig were blind. We verified that there were no responses to light before doing the surgery, obviously. And then we basically do electrical visually evoked potential by implanting electrodes. So, you know, for those of you who work with PIC, this is just a nightmare experiment. So in the end, we used key wires, which are standard wires that are used in orthopedic surgery, to insert it through the bone and reach the occipital part of the visual cortex of the pig. And then we record visual evoked potential before and after surgery. So you can see in the Y that before surgery, there is no response. Why? After surgery, so after having placed the retinal implant with our 10 millisecond light, the evoked potential is recovered. So that means that in vivo, the system works. With that, I would like to conclude this part, and then I still a few slides to show that actually that is the parts that I'm more working on right now. This is really what I want to do. For me, it's really not the point to make the device. I mean, making the device, it's important because we need to make sure that we can make devices that follow the ideas. But really what we want to show is that the visual angle matters. That is really the goal of my research. The visual angle matters. And here you see now the same simulation that you have seen before, but with a polyretina-like simulation. Of course, I anticipate it's a simulation. It's not the reality. The reality will be worse, but it just to understand effectively the difference is that when you have a larger view, it's much easier to grasp the object in front of us. It's much easier to understand the space and the layout. Now, someone of you now can point it out. Of course, here is not the visual angle, it's the resolution, because here we have 45, 40, in the simulation is 45, even the real polyretina device is 43, but it doesn't matter. We have 45 degree with 10,000 pixels, no? So what makes it nice is not the size of the visual angle, but it's the fact that we have a lot of pixels, a lot of phosphine. It's a fair comment, and that's why we decide to prove it forward. No, these data are published. I have other unpublished, but this is in virtual reality where you basically compare performance with the same pixel resolution. No, so the pixel resolution is not different, but we just increase the visual angle. We did many tests in virtual reality. Here, the game, I just pick up one, is to cross this busy street, no? And you see that the success rate, which in this type of experiment means survival rate in the end of the day, improves with the visual angle, really. Now, because in one seminar that he hosted in this seminar series with Jim Whelan, there's been a lot of discussion about the visual angle, no? How it should be. It's the polyretina is 45. Is 45 a magic number? Is a good number? You need more or less. So here I give you my point. Now, of course, if you consider people with peripheral vision loss, 45 degree won't be necessary. Normally, based on my experience, people with peripheral vision loss, typically until they have less than 20 degree, they behave normally. So I hand sketched this line, which somehow represent my understanding in people with peripheral vision loss. No? Until they reach the 20 degree, they perform more or less nicely or normally. Then once the visual field decrease, then they start to have troubles. And it's not a surprise that the WHO set 20 degree as a threshold for blindness, because it's really when you see the impairment. But don't forget that those people, they have remaining central vision, which is normal vision or pseudo-normal vision. It's anyway much better than artificial vision. If you substitute central vision with artificial vision, then that's why larger visual field it's required, because your capability to grasp details and to take advantage of eye movement to collect images, the classic saccade image forming, it's impaired. And that's why a larger visual angle is necessary. Is then 45 the magic number? You need 60, 100? I don't know. I think that's reasonably depends on the task. For example, in this task, you see that you reach saturation of 35 degrees. 45 doesn't improve much more. We have made other tasks where there are improvements. I think it depends on the condition on the task. The same thing for people that simulate natural peripheral vision loss. Now, depending on the difficulty of the task, they figure out that the threshold was 20 degrees or 5 degrees or 15 degrees. That was its task complexity related. But my point is that when vision quality decrease, like in artificial vision, then the visual angle matters more. That is my point. And you see it here in this experiment that we are doing in the street lab in Paris. Basically, the subject has to perform a task, now going from home to the ATM, then to the post office, and then go back to home. And we are measuring several parameters, but what I can show in artificial vision, or this is augmented reality, but what I can show you here, one thing, because visually it's very easy to grasp, here is with 20 degree poly rate in artificial vision. This is the performance, one performance with 45 degree poly rate in a vision. You clearly see that the green is when the subject is on a path which is allowed or safe. So either on the walk side or on the crossing path. And the red one is somehow hanging in the middle of the street where it should not be. And you clearly see that by increasing the visual angle with the same pixel resolution or the same phosphene resolution, that parameter improved dramatically. Of course, we made other tests like performance on task and they all improved. But here is very, very clear that the visual angle matters. And perhaps 45 degrees is not even enough because there are still moments where they are confused somehow. Okay, so in the last few minutes, I want first to acknowledge all the people that have taken part in this journey on the retinal implant. Here you have a list of papers where those data have been taken if you want to watch them more carefully, more in details. Now, in the last 5 minutes, I want to move forward into new things. In the lab, we have developed a variety of visual implants, a retinal implant. We developed an optic nerve implant, which we believe is still a very good idea. What we are limiting us in the optic nerve stimulation is the main limiting factor for me is the capability to miniaturize electrodes. The electrodes cannot be made as small as we wish. That is, there is a physical limit. And for making an optic nerve implant a valuable option with a lot of electrodes integrated in the optic nerve, we will need to miniaturize beyond materials capability limit. So that is the physical limit that we have. And very recently, we moved into cortical implant. The reason, but we keep our flavor to a certain extent. For me, the flavor is always visual field or artificial visual field matters. So I would like to have a cortical implant capable to restore a large visual angle. And that is a challenge. It's a dramatic challenge because the retina is big somehow. No? You can place electrode all around and you have a large visual angle. Also, the visual cortex is somehow big, but there is the cortical magnification. Most of the visual cortex, in particular, the accessible part of the visual cortex, is just mapping a small layer around the fovea, very few degrees. Most of the rest is mapping the interhemispheric area, and probably even more difficult in the calcarine fissure, which is inaccessible. So it's very difficult to think about covering, really, even in terms of anatomical space, to have space to put electrodes. Don't think about the technology for the moment, just space to cover a large visual angle. So some people hypothesize that, well, you can actually do it if you, this was a simulation made some years ago. You can combine different visual cortex, like for example, V1 for the central macular area, then the dorsal one, then V1, the interhemispheric, give periphery, and then V2 and V3 and so forth, and you can build a large visual angle. Now, of course, yes, the challenge is to understand how phosphene generated in V1, V2, V3 will sum up together, conflict each other. We know a lot about V1. We don't know much about shaping phosphene in V2, V3, temporal resolution. There is a lot of questions to be solved here. But the point is that maybe it's possible to have a large visual angle. But now the key problem became the technology. Then it's a technological problem. Because I kind of reviewed and I apologize if I didn't put here everything, but those are representative. Those are 4 projects and I felt obliged now to add Neuralink since they disclosed that they are going into visual cortical prosthesis. So the UTRA was made as a visual cortical stimulator, but we know it's and by the way, I only selected the penetrating device, not the surface device. But we know it's very tiny. With the UTRA, you typically get phosphine in 2 by 2 degree of visual angle around the macula. So it's a tiny visual angle. And it's not wireless, it's wired. We have the Neuralink. Then we have new device like the Gennaris and the intracortical visual project by Philip Troik. By the way, they are conducting, with this device, they are conducting the first patient as we speak. They implanted 25 of this module in 1 patient. They have nice results, but still those modules are very bulky. Each module is big. There are few electrodes per module. So in the end of the day, the overall density, they will like mostly patchy vision. One module generates a patch of artificial vision, and then the other module is separated, generates other patches. It's like a very patchy things. I coming from the experience with polyretina, where you can build a device and put electrodes where you want, almost in an unlimited manner with the photovoltaic things. Of course, we cannot make it as small as we wish. There are physical limitations. That's to be clear. But we can basically put electrodes by design where we want. These devices were a bit constrained to me. I spent really years to think about how to change the paradigm here and to make it more similar to polyretina. Of course, I can't use photovoltaics. So we decide, because it's not transparent, so we decide to make basically individual electrodes of the UTRA. So basically, imagine this is a UTRA. You divide it into individual electrodes, and each electrode is now a CMOS device, very tiny, 250 by 250 micron, which has everything required to receive signal and provide stimulation to the cortex. So that's the idea we are focusing. So we made we are not yet tested in animals, but we made the device. So here it's our first electrode. You see it's a CMOS chip with the 2 electrodes. If you want the stimulating and the return electrode, it's a local return scheme. And actually we're pretty good because we can miniaturize a lot the technology. So compared to other wireless stimulation technology, we are fairly much smaller, and that is important for at least the central part of the visual cortex. We want to put them with 400 micron pitch as the UTRA. We need to, we are decent here, but we need to improve and work a little bit more, because so far we can control 1000 chip or 1024 to be more precise. It's good, but it's not enough. We need more. If you think about large visual, basically with 1000 we cover 14 by 14 millimeter square, which is not a lot in terms of visual angle reproduction. So we need to increase this number. We need to boost a little bit the current that can be wirelessly generated. Here we can generate a little. For the moment, our ceiling is 40 micron. It's good, but we would prefer to have more. So that's our parameter that we are working on. But that is a little bit the concept that we are following. So the idea is that these modules that can be somehow put into the cortex with almost wide surface with an unlimited number, theoretically speaking. And here you really see the chip. Inside you see the coil, all the electronics to drive the stimulation, the coils to receive the stimulus. And here I would like to acknowledge my collaborators in this project. So with that, I conclude. I just briefly acknowledge the sponsors for these activities. And most importantly, I would like to thank my group that evolved over the years. And I would like to thank you for hosting me and to listening to the talk. And with that, I'm very keen to take any question you might have.
Okay, thank you, Diego, for this great talk. Very interesting. So let's all unmute ourselves and thank Diego. And we can start with question. Maybe I will begin with the first one. How do you separate? So this is something that many people do, but what is your way to separate between direct stimulation of the retina and the current artifact I mean, this is sometimes can
Ah,
be very, very tricky. It's
no,
always
no,
very difficult. You have to take some of the, and mainly because you are doing 10 milliseconds of stimulation, then how can you distinguish between the artifact and the?
yeah, very good question. Just give me a second. Well, I don't have a zoom in, but basically, no, I don't have a zoom in, but basically, so what we do is so the artifact is very visible, is big and visible, no? Normally, we see spikes. So basically, it's manually done. There is no automatic system. The student did it. Well, there was a first threshold and then verified everything one-to-one. That's the reality. It was manually done. But to make it a little bit more precise, so the artifact is very visible. And then normally we see spikes 1 milli, because we know now, unfortunately, I don't have the zoom in, but in the paper, in the first paper in the 2018, there is a figure where there is the zoom in, no? And the artifacts are very visible at the onset and the offset of the light, right? So it's not a 10 millisecond long artifact. You get it at the very visible at the onset and the offset, because there is a low pass, there is the filter, obviously, of the amplifier. And then in the paper, there is a figure where you clearly see a spike within the bar. No? So we can detect direct activation. Now, the question is how good we can detect them. Obviously, the first, and here we're mostly interested in the first artifact, the onset artifact, the first millisecond of the light is completely blank. So to say that every spike might occur within the first millisecond, roughly speaking, if there is any, it's lost. So we are not able to get it. We try to do on the other hand, I must add that we try to do the approach that was developed or used by E.J. Ciciniski, no? You know, he kind of have the blank and the artifact with a little deformation, no? And by subtracting the blank, that was an artifact. We did the same, but in our recordings, we never, I mean, basically always came out to be just artifact. Never sure, but I cannot say for 100% sure because the artifact is tricky. So it might be possible that we are missing some direct spike. That is, it's a possibility. On the other hand, we see some of them. So especially at very high intensity.
And
so it's not a precise science.
Yeah. Because it's very challenging to know. Another thing is, did you have any chance to look for longer period of time to see what would be the effect of such a big implant obstructing actually the vitreous from the retina, or the fluid from the retina? I guess you are doing vitrectomy, and are there any changes with this, because it's a huge implant?
No, so the short answer is no, because we kept the peaks for only 2 weeks. Or no, actually, some of them were kept for 1 month. But now the immediate consequence that we saw, which is not necessarily related to the problem you were mentioning, but the immediate one in one animal, we saw. I don't know if now I use the correct terminology, and apologize for that since it's recording, but you know, I'm still an engineer. But you see that when the vitreous, because of course you have fluid, no, and then there is what is called vitreal proliferation somehow. You see some sort of tendon, which are not tendon obviously, but sort of line that start from the implant. That's we observe it, and it's clearly it's a known fact thing, so it was expected. It's something that we have to deal with in the long term, definitely. About the nutrient supply to or the exchange from the vitreous to the or whatever fluid to the retina, that is another good point. But likely the solution is somehow comes from engineering, so I'm more comfortable with that. Well, the new generation of the implant that I don't have yet here, but it's much thinner. So this is quite thick. This implant in the central part is 700 micron thick. it's less thicker in the periphery, but in the center is 700 microns. It's very thick. The new implant is much thinner. I can say that it's less than 100 micron, so it's very easy to create porosity in it. Whether this is going to help solve, I'm not sure, that's the strategy that we are taking.
Having little holes.
Yeah, correct.
Okay.
We have small and large holes, depends on the position.
Okay. Thank you very much. Any other questions? No other questions? Okay. So thank you, Diego. This was really exciting talk, and looking forward to meet you in one of these conferences. So let's all thank again, Diego.
Thanks a lot for having me.
And thank you very much for this talk, exciting talk. Thank you.
Thank you. Bye.
Thank you.